Okay, so let us start. It is next chapter, that is thermodynamics. See here, the first law of thermodynamics, which already we know. So we'll just see it in the brief. That is, whatever amount of energy is applied to the gas is used up by the gas in two different ways. That is the change in internal energy and the work done. One part is used to increase the internal energy of the gas, and remaining part always is used to do the work against external pressure. So that's why we get this as dq is equal to du plus dw as the expression for first law of thermodynamics. Okay, so and here we can note here that this dq and dw are actually the path functions. जैसा कि लास्ट टाइम भी मतलब चैप्टर के टाइम भी हमने बताया था कि ये जो dq और dw जो होते हैं तो वो दोनों कौन है, path functions है. That means they depend on the path. Okay, but this du is actually the state function. It doesn't depend on the path followed by the system. तो कोई भी प्रोसेस जो है तो वो अगर इसका इनिशियल पॉइंट और फाइनल पॉइंट अगर सेम है तो उस केस में du will be the same. We can be sure that the change in internal energy will be the same irrespective of dq may be different and dw may be different. ठीक है, मतलब dq जरूरी नहीं कि वो सेम ही होगा, dw भी जरूरी नहीं कि वो सेम होगा, बट du जो है वो जरूर सेम ही होगा. मतलब अगर सपोज ये x एक्सिस y एक्सिस और सपोज एक पॉइंट से दूसरे पॉइंट पे सिस्टम को हम लेके जाते हैं, इस पाथ से एक बार लेके जाते हैं और दूसरे वाले पाथ से इस पाथ से लेके जाते हैं. ठीक है, तो दोनों पाथ के अंदर du1 और du2 ये जो भी इंटरनल एनर्जी चेंज हुआ तो वो du1 is compulsorily has to be same as du2, no doubt. बट इस प्रोसेस से फर्स्ट प्रोसेस में जो वर्क डन हुआ उसको हम बोल सकते हैं सपोज dw1 और सेकेंड प्रोसेस में जो वर्क डन हुआ dw2, that need not to be equal. dw1 need not to be equal with dw2 here. And even the amount of heat absorbed in the first process is suppose dq1 and the amount of heat absorbed in the second process is suppose dq2, then again this dq1 need not to be same as dq2 here. That means the amount of heat absorbed and work done, these two are just the path functions. They depend on the path actually. But on the other hand, the change in internal energy is actually the state function. It depends only on the state and not on the path. Okay, so dq इतना अगर हीट हमने इसमें ऐड किया तो उसकी वजह से कुछ पार्ट जो है वो उसका इंटरनल एनर्जी का चेंज बन जाएगा. If suppose u1 is the initial internal energy and suppose u2 is the final internal energy, then we can say that u1 plus, okay, we can understand this. Okay, so amount of heat added is equal to the change in internal energy plus work done. That is the first law of thermodynamics. और इनके साइन कन्वेंशंस भी तुमको पता होने चाहिए. साइन कन्वेंशंस, आई होप ऑल ऑफ यू आर नोइंग दिस साइन कन्वेंशंस. देखो, चेंज इन इंटरनल एनर्जी जो है वो कभी पॉजिटिव रहता है जब इंटरनल एनर्जी बढ़ता है. तो अगर फाइनल एनर्जी इज ग्रेटर देन इनिशियल इंटरनल एनर्जी, then we can say that du or delta u will be positive. Okay, but if suppose the final internal energy is less than the initial one, then we can say that du or delta u is going to be negative. Okay, ये बात अच्छी तरह से याद रखो. और वर्क डन के बारे में भी, if work is done by the system, by the gas during expansion, so if there is a expansion of the gas, then work done is going to be positive. ओके, एक्सपेंशन के दौरान वर्क डन पॉजिटिव हुआ करता है, बट इन केस ऑफ द कंप्रेशन द वर्क डन विल बी नेगेटिव, remember. So work done will be positive or negative depending upon whether there is expansion or compression. Expansion means like work is done by the gas, which is considered as positive, but compression means work is done by the surroundings on the gas, and that's why it's going to be negative. And dq के लिए साइन कन्वेंशन इजी है, if the amount of heat is added to the system then it will be positive, and if suppose the amount of heat is extracted from the system then it will be negative. Okay, dq will be positive if the heat is given to the system, to the gas in this case, and it will be negative if the heat is extracted from the gas. That is we have discussed just now. These are the limitations of thermodynamics, law of thermodynamics. थर्मोडायनामिक्स के अंदर हम फर्स्ट लॉ से ये हमको कभी नहीं पता चल सकता कि हीट कहाँ से कहाँ तक फ्लो होगा, ठीक है। और दूसरा कि इफिशियंसी जो है, इफिशियंसी के बारे में ये बता नहीं जा सकता, क्योंकि इफिशियंसी के बारे में सेकेंड लॉ ज्यादा बात करता है। Yes, now we'll see the important concept here, that is the specific heat of the gas. जैसे कि हमने ऑलरेडी देखा है कि specific heat of the substance is defined as the heat required to raise the temperature of unit mass of substance through 1 degree Celsius or 1 Kelvin, and C is defined as 1 upon m into dq by dt, no doubt. But गैस के लिए क्या होता है, दो स्पेसिफिक हीट्स बनते हैं, ठीक है। ये स्पेसिफिक हीट का जो वाटर का स्पेसिफिक हीट विथ रिस्पेक्ट टू टेम्परेचर इस तरह से चेंज होता है। Okay, we can see the amount of heat supplied to the gas at constant pressure and constant volume. So at constant volume the specific heat is denoted by Cv, and at constant pressure it is denoted by Cp. So this is the formula for specific heat, principal specific heat for the gas at constant volume. And specific heat at constant pressure is given by Cp is equal to 1 upon m into dq by dt. Okay, then molar specific heat at constant volume and molar specific heat at constant pressure, जो कि हमने ऑलरेडी देखा था कि the amount of heat required by the gas to increase its temperature, 1 mole of temperature of 1 mole of the gas through 1 degree Celsius will be denoted by capital Cv, and this capital Cv will be related with small cv by this relationship. See it here, capital Cv is always equal to m into small cv. तो ये relationship है इन दोनों के बीच में. In the same way we have that molar specific heat at constant pressure, which is nothing but the amount of heat required for to raise the temperature of 1 mole of a gas through 1 Kelvin or 1 degree Celsius, and this is also related with small cp. तो capital Cp is always equal to m into small cp. ये हमको इन दोनों के बीच में का जो रिलेशनशिप है तो वो याद रखना अच्छी तरह से. Cp is always greater than Cv, ठीक है, ये हमने ऑलरेडी देखा है, जस्ट फॉर रिवीजन. We also have seen this relationship between the Cp and Cv from the first law of thermodynamics only. देखो जब हीट सप्लाई किया जाता है dq इज इक्वल टू Cp इंटू dt हम लिख सकते हैं, और yes, only this table is worth noting actually, जैसे हमने लास्ट टाइम भी देखा था और बहुत सारे एमसीक्यूज भी उसके ऊपर सॉल्व किए थे। मोनोएटॉमिक, डायटोमिक, उसमें भी डायटोमिक, वाइब्रेटिंग एंड नॉन वाइब्रेटिंग। Now we see some processes. Okay, isothermal process, we'll see it in detail. Okay, what is isothermal process? The process in which the temperature remains constant will be called as the isothermal process. And since the temperature remains constant, we can also say that the internal energy is also constant, and the change in internal energy in this case will be zero. Remember. तो अब यहाँ पे ये अलग अलग प्रोसेस हम देख सकते हैं इस थर्मोडायनामिक्स के अंदर, जैसा कि आइसोथर्मल प्रोसेस है, क्वासी-स्टैटिक प्रोसेस है, आइसोकोरिक प्रोसेस होता है, एडियाबेटिक प्रोसेस होता है, साइक्लिक प्रोसेस होता है और आइसोबारिक प्रोसेस होता है। तो ये सब प्रोसेस हमको एक एक करके डिटेल में देखने हैं। देखो सबसे पहले अगर हम देखेंगे व्हाट इज क्वासी-स्टैटिक प्रोसेस, इट इज द स्लो प्रोसेस। ठीक है ना, क्वासी-स्टैटिक प्रोसेस मतलब द प्रोसेस व्हिच टेक्स प्लेस वेरी स्लोली. It takes place so slowly that at every point the system and surroundings are in equilibrium with each other. Okay, the changes that take place are very small. They are so small that we can consider almost to be same. तो जैसे आप यहाँ पे हम देख सकते हैं कि यहाँ पे जो इंटरनल प्रेशर जो है और टेम्परेचर जो है, तो वो उसका प्रेशर P है और टेम्परेचर T है। ठीक है, और सपोज कि बाहर का जो प्रेशर है, सराउंडिंग्स का जो प्रेशर है, तो वो भी P और टेम्परेचर भी T है। बट सपोज दैट वी इंक्रीज द प्रेशर ऑफ सराउंडिंग्स बाय डेल्टा P, then we can see that the pressure of surroundings will be P plus delta P, which is very small, slightly greater than the pressure of this system here. P से बहुत थोड़ा ज़्यादा है। Similarly, this temperature of system is going to be T. But if we change the temperature of surroundings by a very small amount, that is delta T here, then we can see that the T and T plus delta T are almost going to be the same. So in this process, मतलब ऐसे हालत में जब ये इस तरह से जो प्रोसेस कैरी आउट किया जाता है, जब हम चेंजेस जो करते हैं वो चेंजेस बहुत छोटे होने चाहिए. The change should be so small that it can be neglected as compared to the actual value of that quantity. Then in that case we can call it as a quasi-static process. Remember. So for example, the piston is moves down very slowly, such that at every stage the difference between the system pressure and surroundings pressure is delta P, which is going to be very small. Okay, even the temperature difference also, the temperature difference between the system and temperature of surroundings, that is delta T, is also going to be very small. So, and this happens at every step, not only at one step only. This should happen at every step. Then only we can call it as a quasi-static process. The second in the list is the isothermal process. See here, isothermal process, which is the process at which the temperature remains constant throughout. पूरे प्रोसेस के अंदर टेम्परेचर जो है वो कांस्टेंट रहना चाहिए, उसको हम बोलते हैं आइसोथर्मल प्रोसेस. रिमेंबर, आइसो का मतलब होता है कांस्टेंट और थर्मल मतलब टेम्परेचर. ओके, सो जब टेम्परेचर कांस्टेंट होता है तो सीधी सी बात है कि the pressure will be inversely proportional to the volume. That means P is inversely proportional to V, which is also called as the Boyle's law. So Boyle's law is obeyed in case of isothermal process, or we can say that PV remains constant at constant temperature in case of this isothermal process. Remember, अभी जबकि isothermal process के अंदर temperature ही constant है, तो उसकी वजह से क्या हम बोल सकते हैं कि internal energy will also remain constant, and hence the change in internal energy is also going to be zero. So remember, in case of isothermal process, du remains zero. So if we use this in the first law of thermodynamics, then we can say that since du is equal to 0, dq is exactly same as dw. That means whatever work is done is is at the cost of whatever amount of heat is provided to the system. तो गैस को जो भी हम हीट प्रोवाइड करेंगे, तो उस वो हीट को यूज करके वो क्या करेगा, पूरा का पूरा वर्क डन करेगा, पूरा का पूरा वर्क डन में वो कन्वर्ट करेगा. नो चेंज इन इंटरनल एनर्जी विल take place here. Yes, this is one of the important thing, that in case of isothermal situation or process, the bulk modulus of the gas remains equal to pressure exerted by the gas. Okay, that is also we have to see in the next slides. Okay, so specific heat of the matter is infinity. ये भी important बात है, देखो यहाँ पे कि isothermal process के अंदर जो specific heat है गैस का infinity होता है. क्यों? क्योंकि specific heat का definition ही क्या है? How the specific heat is defined? The specific heat is defined as the amount of heat required to raise the temperature through 1 degree Celsius. So यहाँ पे n into dt आएगा कि नहीं? dt. But यहाँ पे dt तो 0 है. Since dt is 0 here, the denominator becomes 0, and any fraction in which the denominator is going 0 remains infinity. That's why we can say that the specific heat of the gas under isothermal condition is infinite. Okay, यहाँ पे हम देख रहे हैं, देखो dt is going to be equal to 0, so therefore this C will actually be equal to infinity in this way. And work done in this gas by the gas here in this case is always maximum in case of isothermal process. Okay, suppose that the piston is lifted from this point to this point here, and it is the initial position and this is the final position, and suppose that the distance between these two is dx, and here the volume change in volume of this gas will actually be area into dx. ये हम समझ सकते हैं आराम से. ओके, तो अभी इसमें देखो कि फ्रिक्शनलेस पिस्टन के द्वारा जो वर्क डन किया गया है, तो वो वर्क डन कैसे हम निकाल सकेंगे? इस स्मॉल स्टेप के अंदर यहाँ से लेके यहाँ तक का जो स्टेप है, इस एक स्टेप के अंदर कितना वर्क डन किया, तो वो निकाल सकेंगे आराम से बाय यूजिंग दिस P प्रेशर इनटू dV. तो जो हमारे पास फॉर्मूला है वर्क डन का, dW is always equal to P into dV. Okay, but dV, as we have just now seen, that dV is going to be actually equal to A into dx. Okay, तो यहाँ पे हम dW को क्या लिख सकते हैं? P into A into dx ऐसा लिख सकते हैं याद से. और फिर यहाँ पे इसको इंटीग्रेट करना हमको जरूरी होगा, क्योंकि यहाँ पे प्रेशर जो है वो वेरिएबल है. ठीक है, तो इन केस ऑफ द isothermal process the pressure is variable, and that's why we have to integrate this equation from V1 to V2. V1 is the initial volume and V2 is going to be the final volume. So if we just work this out, तो हमको यहाँ पे P के बदले RT upon V लिखने आएगा. तो अगर हम वहाँ पे रिप्लेस कर देंगे उसको आइडियल गैस इक्वेशन यूज करके, तो यहाँ पे दिस इज फॉर 1 मोल एक्चुअली. सो वी कैन से दैट दिस W is equal to integration of P into dV, where P के बदले हम क्या रखने वाले हैं? RT upon V रखने वाले हैं. तो इससे वो बन जाएगा integration of RT upon V into dV, where RT is a constant and dV upon V is just left inside the integration sign. And as we know that the integration of 1 upon x, ठीक है ना, 1 upon x का इंटीग्रेशन क्या होता है? तो वो होता है log of x, बराबर. So इसलिए यहाँ पे ये 1 upon v dv का इंटीग्रेशन क्या मिल रहा है हमको? Log of v, and that is from v1 to v2. So if we replace v2 here, so we get this log of v2, and if we replace v1 here, then we get this log of v1. And as we know that this log of a minus log of b is actually log of a upon b. So we get this as log of V2 upon V1 as a final. This is only for 1 mole. Okay, so but if suppose we have to find it out for n moles, then this n will also appear here. यहाँ पे n आ जाएगा. तो और लेकिन यहाँ पे ये जो है ना log to the base e है, right? But if you want to convert this into the log to the base 10, then we have to multiply it by 2.303, and hence we get this work done W is equal to 2.303 into RT log V2 upon V1. Again, this is for 1 mole only. But if we have that, so okay, one more thing is that, see, V2 upon V1 can also be expressed in terms of P1 and P2, because we know that P1 into V1 is equal to P2 into V2. So ये जो Boyle's law है, तो वो अगर हम यूज करेंगे तो इससे हमको क्या मिलेगा? देखो, V2 upon V1 can be proved to be equal to P1 upon P2, and hence this equation can also be modified as 2.303 into RT into log of P1 upon P2, where P1 and P2 are the initial and final pressures respectively. Again, this is for 1 mole. Remember, for n moles, it will look like W is equal to 2.303 into nRT into log to the base 10 of V2 upon V1. Okay, and this is in terms of P1 and P2, it will be simply 2.303 nRT into log of to the base 10 P1 upon P2. दो तीन शॉर्टकट्स भी यहाँ पे याद रख लो कि अगर सपोज वॉल्यूम जो है वो अगर डबल हो जाता है, if suppose V2 is going to be 2 times of V1, then in that case we can say this W will get modified as 2.303 into nRT into log of T2 upon T1, where, sorry, V2 upon V1, where V2 is going to be 2 times of V1. So here log of 2 will be left as it is to the base 10. And as we know that this log of 2 to the base 10 is going to be 0.3010. So we can just replace it by that and get this 2.303 nRT into 0.3010, which when multiplied together comes out to be 0.693 into nRT. ये 693 जो नंबर है वो भी तुमने अभी केमिकल काइनेटिक्स के अंदर देखा रहेगा. ठीक है, 693 हाफ लाइफ पीरियड के अंदर, राइट? एंड इसका रीजन भी वही है कि actually it is the product of this 2.303 and 0.3010, which is a log of 2 to the base 10 and 2.303, which is the conversion factor of log of to the base e to the log of to the base 10. Okay, ये बात अच्छी तरह से याद रखो. And also that see, दो तीन चीजें हमको यहाँ पे अच्छी तरह से याद रखनी है इस फॉर्मूला के बारे में. When this W will turn out to be positive, and when it will turn out to be negative. So in the broad sense, we'll see if V2 is greater than V1, then the ratio of V2 to V1 is going to be greater than 1. And since the ratio is greater than 1, we can say that this log of this whole thing is going to be positive, because log of 1 is 0, correct? Log of 1 is 0. So log of any number which is greater than 1 is always positive. So work done will always be positive when V2 is greater than V1. But if suppose V2 is less than V1 on the other hand, then in that case we'll see that the ratio of, see here, the ratio of V2 to V1 will always be less than 1 in that case, and hence so the log of any number which is less than 1 is always negative. So then work done will be negative, and because of that a minus sign will appear here. ठीक है, तो ये वर्क डन के लिए माइनस साइन आएगा यहाँ पे. In the same way we can talk about P1 and P2 also. This V2 is greater than V1 means P1 must be less than P2. In both of these situations work done will be positive. But in the case when V2 is less than V1 or P2 is greater than P1, so in that case the work done will be negative, no doubt. Yes, that is what just discussed here. आइसोथर्मल प्रोसेस के अंदर dP by P कितना होता है? माइनस ऑफ डेल्टा V by V होता है. Just forget about the MCQs. Yes, now we'll see the adiabatic process. Okay, what is adiabatic process? The process in which the amount of heat released or absorbed by the system is going to be zero. That is called as adiabatic process. Remember, no heat is absorbed or evolved from the gas or system in general, then it is called as the adiabatic process. So since the heat is not absorbed or evolved, whatever work is done is at the cost of the change in internal energy of the gas. That means if work done is positive, then change in internal energy will be negative, and if work done is negative, then the change in internal energy will be positive. मतलब change in internal energy du और work done dw, क्योंकि क्योंकि देखो dq is equal to क्या होता है, du plus dw होता है, बराबर. But dq is going to be zero here. Since dq is zero, so sum of du and dw must be zero, which only takes place when du is going to be minus of dw, or dw is going to be minus of du. Means dw and du are always negatives of each other. And also that the pressure and volume are related by to each other by using this equation here. P into V raised to gamma is always constant in case of adiabatic process. Okay, and this can also be proved in a very simple way. Consider a gas which is thermally insulated and undergoes an adiabatic process. Suppose that the volume changes by dV. Okay, वॉल्यूम चेंज कितना हो गया, dV हो गया, तो वर्क डन कितना होगा उसके द्वारा, P into dV इतना वर्क डन होगा. ठीक है, और ऐसे हालत में देखो ठीक से, the change in internal energy of the gas will actually be equal to 1 into Cv into dt for 1 mole only. So it will be actually Cv into dt, no doubt. And hence in case of the यहाँ पे जबकि dq 0 होता है और du जो है ये इसका वैल्यू हमको मिल रहा है, और dw का जो वैल्यू है वो हमने लास्ट स्लाइड में देखा था, dw that is the work done. देखो work done is this much, p into dv, this is the work done, and du is going to be cv into dt for 1 mole. Okay, we are considering the 1 mole only. Then we can say that this du plus dw is equal to 0, which means if we replace it by that, the value of du is going to be cv dt here, and so it is replaced here, and dw का वैल्यू जो है वो p dv है जो हमने यहाँ पे रिप्लेस कर दिया. तो नेक्स्ट स्टेप में देखो क्या बनेगा. Yes, if we just have this pv equal to rt and just differentiate it once, then we can get that. अब देखो इस pv equal to rt को अगर differentiate करेंगे तो यहाँ पे हमको मिलेगा d by dv of p into v, which must be equal to d by dv of rt, right? So that here d by dv of pv, मतलब प्रोडक्ट रूल यूज करना पड़ेगा यहाँ पे, तो यहाँ पे हमको मिलेगा p into v का डेरिवेटिव which is dv by dv plus v into p का डेरिवेटिव which is dp by dv, and that is going to be actually equal to r is constant and here it will be dt by dv, and if we just multiply this throughout by dv, then this dv 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 will just get cancelled, and what we are left with is p into dv plus v into dp is equal to r into dt. That is what we have written it here. Okay, p into dv plus v into dp is equal to r into dt. From this we have to find the equation value of dt here. As we can see here, dt is actually going to be this whole thing divided by r. Okay, and this value of dt is going to get substituted in the equation which we have just seen now. अभी जो लास्ट स्लाइड में हमने इक्वेशन देखा था, du plus dw इक्वल टू 0, इससे हमको मिला था cvdt plus pdv इक्वल टू 0. तो यहाँ पे pdv के बदले हमको ये dt के बदले हमको ये डालना है, dt के बदले ये पूरा उसका जो वैल्यू है वो हमको रिप्लेस करना है, जिससे हमको मिलेगा cv into pdv plus vdp divided by r plus this pdv kept as it is here, and that is equal to 0 as it is here. And then we'll see in the next step here we can just multiply throughout by r so that this r can be written here, and in the next step now we can substitute the value of R. ओके, R के बदले क्या हमको लिखना है, Cp माइनस Cv लिखना है, ठीक है। देखो ठीक से यहाँ पे हमको ये जो Cv इंटू PdV प्लस VdP एज इट इज, ओके, V इंटू DP एज इट इज प्लस R इंटू R के बदले हमको क्या रखना है, R को ही हमको डालना है Cp माइनस Cv। ओके, तो देखो यहाँ पे हमने R के बदले डाल दिया Cp माइनस Cv इंटू PdV एज इट इज, सो दैट व्हेन वी ओपन दिस ब्रैकेट, ओके, ये ब्रैकेट जब हम ओपन करेंगे तो होगा क्या, देखो कि नेक्स्ट स्टेप में हमको मिलेगा Cp इंटू PdV प्लस Cp इंटू VdP, करेक्ट है, प्लस Cp अगेन इंटू PdV माइनस Cv इंटू PdV, करेक्ट है। सो दैट हियर दिस Cp इंटू PdV, ये देखो Cv इंटू PdV, तो इसमें से हम कॉमन क्या ले सकते हैं, ये देखो PdV कैन बी टेकन कॉमन and hence this PdV multiplied by Cp minus Cv, okay, that is going to be equal to 0, yes। See the next here, so R के बदले हमने यहाँ पे डाल दिया Cp minus Cv and ब्रैकेट ओपन किया, तो देखो Cp इंटू PdV माइनस Cv इंटू PdV, तो अभी इसमें क्या हो रहा है, देखो ठीक से ये Cv इंटू PdV and minus Cv into PdV will just get cancelled, right, and what we are left with is simply ये टर्म और ये टर्म बचा रहेगा, जिससे हमको मिलेगा Cv into VdP plus Cp into PdV, that is equal to 0। if just we shuffle these terms, then we can just arrange it as dP by P plus Cp by V into dV by V, okay, but as we know that this Cp by Cv मतलब ये क्या, गैमा, ठीक है ना, तो Cp by Cv को हम गैमा लिख सकते हैं, तो इससे हमको ये मिलता है dP by P plus gamma into dV by V is equal to 0। and now if we just integrate both sides, so integration of dP by P becomes log P here, gamma is a constant as it is, and this integration of dV by V here becomes log V actually, and now we can just take the next step here, so log P plus gamma log V equal to constant means log of P plus यहाँ पे gamma जो है वो ऊपर चला जाएगा V के पावर में, जिससे हमको मिलेगा log of V raised to gamma, that is equal to constant, and as we know that log of A into log of B is going to log of AB, तो इससे हमको मिलेगा log of this P into V raised to gamma is going to be a constant, and since log of something is constant means that same thing will also be a constant, that gives P V raised to gamma is equal to constant as a final equation, and also we can prove the relationship between V and T using the same thing. If we use PV equal to RT here, then we can substitute the value of P here in case of PV raised to gamma equal to constant and get it as RT upon V into V raised to gamma equal to constant. So V raised to gamma upon V becomes V raised to gamma minus 1, and R is a constant, can be taken in the other side so as to become new constant, so as to get it as T into V raised to gamma minus 1 is also going to be a constant, remember. And relation between P and T can also be derived on the same lines, that is PV equal to RT यूज करेंगे और P को रिप्लेस करेंगे RT by P से, और जो अभी हमने प्रूव किया था कि PV रेज टू गैमा इक्वल टू कांस्टेंट, तो उसके अंदर अगर V के बदले RT by P डाल दिया तो वो बनेगा P into RT by P the whole raised to gamma। If we separate out and simplify this further, we can prove that P raised to 1 minus gamma into T raised to gamma is always a constant, or we can also write it as t raised to gamma upon p raised to gamma minus 1, because gamma is always greater than 1, remains a constant. ये भी उसका ही अलग फॉर्म है लिखने का. Even we can also write it as p raised to gamma minus 1 upon t raised to gamma is also constant. ऐसा भी हम इसको लिख सकते हैं, no problem. Now remember this adiabatic process. In case of this adiabatic process, the heat energy is neither it is absorbed nor it is released, and that's why heat absorb करने के लिए थोड़ा time लगता है. But यहाँ पे heat absorb नहीं होने वाला है. Heat is not absorbed. So actually this is a quick process, sudden process. So whenever the sudden changes in pressure are there, then we can call it as a adiabatic process. For example, sudden compressions or sudden expansions, or suppose एक cycle tire tube जो होता है वो अगर burst होता है, तो जैसे वो burst हो गया, तो that is there is going to be a adiabatic process here. So in this case, yes, sudden expansions or sudden compressions are going to be the adiabatic processes, and hence we can note in the examples or even daily life में हम ये note करते हैं यहाँ पे कि whenever there is a sudden expansion, it accompanied by the fall in temperature, and whenever there is a sudden compression, there is a rise in temperature. The temperature rises or falls accordingly whenever sudden compression or rarefaction takes place. Okay. These are the examples. Just forget about that. Yes, one more thing is that here adiabatic process के अंदर bulk modulus कितना होता है? Gamma times pressure के बराबर होता है. याद रखो ठीक से. And in this case, the specific heat of the gas is always 0, just because, see, the specific heat is defined as 1 upon m into dq by dt, right? But here dq itself is 0, right? And since dq is 0, the 0 divided by anything is going to be 0. And that's why in case of adiabatic process, the specific heat is always 0. Adiabatic bulk modulus is gamma times pressure, and the slope of the curve, मतलब ये जो adiabatic curve जो होता है उसका slope जो है वो slope gamma times p by v होता है, जबकि isothermal condition के अंदर जो slope होता है, slope of pv graph is always equal to the p by v only. नेगेटिव तो होता ही है दोनों, माइनस तो साइन वहां पे ही रहेगा ही हमेशा, but that will be p by v in case of adiabatic process, and the slope of PV graph will be gamma times minus of gamma times p by v in case of adiabatic process. Now we'll see the work done in case of adiabatic process. See here, we'll see it in the fast view because already we have done this derivation in the regular actually. Suppose that V1 and P1 are the initial pressures and T1 is the initial temperature. P2, V2 and T2 are the final pressure, volume and temperatures respectively. Then the work done in the small step will actually be P into dV. But since the pressure is going to be variable, the total work done can be obtained by integrating this P into V dV between the limits V1 and V2. Remember. But here we can know that this P into V raised to gamma is always constant. So what can we say? P is going to be K upon V raised to gamma. So we can use this formula twice. First, for the first situation, that is P1 V1 raised to gamma is equal to constant, and P2 V2 raised to gamma is also going to be constant, K. So we can express this P1 and P2 in terms of V1 and V2 here. So we can just replace this P. See here, ये जो P का वैल्यू है K upon V raised to gamma, ये हमको रखना है यहाँ पे P के बदले, जिससे वो बन जाएगा, देखो, K upon V raised to gamma dV into dV का integration from V1 to V2, which happens to be actually integration of 1 upon V raised to gamma dV. K is a constant, that can be taken out, and 1 upon V raised to gamma cannot actually be written as V raised to minus gamma, correct है? And in the next step, we can have this integration solved as V raised to minus gamma plus 1 upon minus gamma plus 1. According to the formula for integration, that is x raised to n, x raised to n का integration क्या होता है, x raised to n plus 1 upon n plus 1. Okay, and then we can just simplify this further and get this minus gamma plus 1 written as 1 minus gamma here, and if we replace this v2 here in place of v, then we can get this v2 raised to minus gamma plus 1, and minus this v1 is replaced here in place of v again, so that we get this minus of v1 raised to minus gamma plus 1 here. But as we know that minus gamma plus 1 can be written as minus of gamma minus 1, correct है? So we can just write it as that and just write it in the denominator here. So ये जो पूरा फैक्टर है तो उसको हम इस तरह से लिख सकते हैं, हाँ k का वैल्यू हम रिप्लेस कर सकते हैं यहाँ पे, देखो we have just distributed this k inside, so that is k into v2 raised to gamma minus gamma plus 1 and minus k into v1 into minus gamma plus 1, k को हमने अंदर पुश किया. फिर अभी k के बदले जैसा कि हमने अभी भी देखा था कि k is nothing but p2 into v2 raised to gamma, and k is also p1 into v1 raised to gamma, because already we have proved that pv raised to gamma is constant in case of adiabatic process. So p1 v1 raised to gamma and p2 v2 raised to gamma is going to be same as k. So k को हमने यहाँ पे अलग तरीके से रिप्लेस किया और यहाँ पे अलग तरीके से रिप्लेस किया, ठीक है. बट यहाँ पे अगर हम देखेंगे ठीक से तो v2 raised to gamma into v2 raised to minus gamma plus 1 remains v2 only, and here v1 raised to gamma into v1 raised to minus gamma plus 1 remains v1 only, and hence we can get finally the equation for work done for 1 mole to be simply 1 upon gamma 1 minus gamma into p2 minus p2 v2 minus p1 v1 in this way, which can also be written as p1 v1 minus p2 v2 upon gamma minus 1, करेक्ट है. ये उल्टा कर दिया और ये इसको भी उल्टा कर दिया, तो gamma minus 1, because this makes sense because gamma is always greater than 1, remember. And if we use this p1 v1 equal to nrt1 and p2 v2 equal to nrt2, then we can just simplify this further and get this as n upon rt2 minus rt1 upon 1 minus gamma, which can also be written as nr common and t2 minus t1 upon 1 minus gamma. But actually this should be written like this, nr upon gamma minus 1 into t1 minus t2, or simply as nr t1 minus t2 upon gamma minus 1. Again, the sign conventions for this will be that if t1 is greater than t2, then work done will be positive. अब देखो t1 greater than t2 का मतलब क्या हुआ, टेम्परेचर इज डिक्रीज्ड. टेम्परेचर डिक्रीज कब होता है, जब सडन एक्सपांशन होता है. सडन एक्सपांशन के दौरान टेम्परेचर डिक्रीज होता है, और यहाँ पे t1 अगर लेस देन t2 है तो इसका मतलब क्या हुआ, टेम्परेचर बढ़ गया. और टेम्परेचर बढ़ने का मतलब क्या हुआ कि the temperature increases only when sudden compressions are there, and compression मतलब work done is negative. So in this way work done will be positive or negative depending upon t1 is whether t1 is greater than t2 or t2 is greater than t1 here. Next we can talk about the isochoric and isobaric process. They are very simple, just finished in 2 minutes. See, in case of just note this here, PV graph of isothermal change is called isotherm, and PV graph of adiabatic change is called adiabatic. Okay, and yes, dp by dv को अगर हम ये pv equal to constant को अगर हम डिफरेंशिएट करेंगे तो हमको स्लोप मिलेगा. तो वो स्लोप मैंने अभी भी बोला कि स्लोप ऑफ isothermal graph is always minus p by v, remember. But the slope of adiabatic process, adiabatic graph का जो स्लोप है तो वो कितना मिलता है हमको, माइनस gamma टाइम्स ऑफ p by v मिलता है. याद रखो ठीक से, that is the difference. So slope of adiabatic graph is always gamma times of the slope of isothermal graph. Means adiabatic graph is gamma times steeper than isothermal graph. Okay. Isochoric process के अंदर क्या होता है, volume remains constant, so change in volume remains zero, and hence work done also remains zero. and hence we can say that this dq is exactly equal to du, and du can be written as cv n cv dt. जो भी अमाउंट ऑफ हीट एब्जॉर्ब किया जाएगा बॉडी का, वो सिर्फ और सिर्फ टेम्परेचर चेंज करने में ही चला जाएगा. दैट इज कॉल्ड एज द आइसोकोरिक प्रोसेस, एंड वर्क डन तो उसमें होता ही नहीं है बिल्कुल. But we can say that since isochoric process volume remains constant, pressure is directly proportional to the temperature. Remember, in case of isochoric process, the pressure is going to be directly proportional to temperature, and change Cv will actually be equal to du by dt, du by n dt actually. And isobaric process के अंदर क्या होता है? Pressure remains constant, and since pressure is constant, in the formula for work done, the pressure P can be taken out of the integration sign, and we are left with integration of dV from V1 to V2, which happens to be V from V1 to V2, which becomes V2 minus V1, and hence we can say that this P into delta V. This is the formula for work done in case of isobaric process. And as we know that PV equal to nRT, so we can just use this as PV2 equal to nRT2 and PV1 replaced by nRT1, and hence work done can also be written to be equal to nR bracket में T2 minus T1. Okay. Charles' law is obeyed here. Since pressure is constant, the volume will be directly proportional to the absolute temperature. Remember, and the dq, amount of heat absorbed in this case, will be ncp dt, where cp is going to be the amount of the specific heat at constant pressure. And cyclic process, which is the last one, when the system returns to the initial state back, then it is called as the cyclic process. In case of cyclic process, du becomes 0, and since du is 0, we can say that dq is going to be same as dw. Okay, so let us stop here. All these are the processes we have to discuss about in today's lecture. So कल के लेक्चर में हम इसके ऊपर बेस्ड एमसीक्यूज देखेंगे. ठीक है, थर्मोडायनामिक्स प्रोसेस जो हमने आज देखे हैं, तो उनके ऊपर बेस्ड एमसीक्यूज हम करेंगे. चलो ठीक है, सो थैंक यू ऑल ऑफ यू, बाय बाय.